We're going to find out. Then if I get my notification. Yeah, those are supposed to be off, but that's okay. Okay, so I'm under the impression that it's working properly because I really hadn't changed anything, so I'm going to let that be. So let's take a look at this quiz that we just took. So the quiz is here. All right, so let's take a look at it. And then we have this. So again, you're going to grade your own paper. You want to use something that's bold, like either a thicker font, something thick and bright, that's different than whatever you took the exam in, all right? So, I mean, it's just, and it's not an exam, it's really light. Let's say each question is worth 5 points. If it's just completely wrong, you would just say like -5. If it's a little bit wrong, just take off like 1 or 2. If it's 100% right or close enough, you can take off 0, right? So each question is worth 5 points. I think it's a total of 25 points. Is it 5 questions, right? So let's take a look at it, but each one's 5. It says convert the angle in radians to degrees. So we're converting from radians to degrees. We talked about this last time. Did we finish 5-1?
We didn't go through averages. We just did the radians to degrees.
Did we do radians to degrees though?
That's it.
Right? So how do we, what was the conversion? We didn't talk about the conversion from radians to degrees, did we? Okay, so you can give yourself credit for that one. So we'll just talk about it now. So that's what I mean, these are gonna be light. So I think that is one that we're gonna talk about today. So let's just talk about it now. So say this was 10 degrees, right? So what's half of a circle in degrees? Did we talk about that? Like half the circle, remember? Yeah, because if we do a quarter rotation, that's how much? 90, and then if we do half, that's what? 180, right? So half the circle is 180 degrees. I'm telling you now that that's pi radians. So to convert from degrees to radians, is this. So you see how it says, if we have 10 degrees, right, we're going to put that over 1. Since we have degrees on top, when we go to do the conversion, we're going to say pi over 180 degrees. All right? So since we have degrees on top, we do degrees on bottom. The units of degrees cancel. So then we will say 10 times pi divided by 180. This one ultimately becomes pi over 18. So 10 degrees in radians should be pi over 18. Let me glance at the solution. Hang tight. Oh, and then it says, okay. So then it says type an integer or decimal. Oh, wait a minute. Cut to degrees. So we got it backwards. So let's switch it up. I'm moving a little quickly. So it wasn't given to us in degrees. It was given to us in radians, right? So let's start over. So if we have 10 radians, all right, I'm going to put it over 1. We're going to go from radians to degrees, all right? So we're going to say times. The conversion from radians to degrees, I'm kind of giving it to you now. So you can give yourself credit for this one. We're just using this as a platform to talk about this stuff. So then we're going to say what? 180 degrees corresponds to pi radians. All right, so pi is the unit of radians. I'll go ahead and do like this so you can see it better. So then the units of radians cancel. We're going to be left with degrees. So then this is going to be what? 1800 divided by pi degrees. So then we just got to crunch that number. Say it should be 1800 divided by pi. Let's see. Hey Siri, what's 1800 divided by pi?
1,800 divided by 3.1415 is about 572.9577.
72.9. Let me see. 9577, 9577, 572. So then it says rounded to 2 decimal places. So what is that? 96? Not. 572.96. What is the units? Degrees. All right. Okay. So now let's glance at it. And I think we are 572.96. Is that okay? Any questions with that one so far? So you may or may not have known that one right now, because I do remember last time, I think we did just stop just before we got to the conversions, right? So you can just give yourself credit for that one. So you can say, so everybody at least got that one right. So you can say -0 for that one. Let's go to the next one. It says find the central angle theta find the central angle theta which forms a sector of area 24 square centimeters of a circle of radius this. Let me see. Arc length area. Okay. So I don't think we talked about this one, so I'll just tell you this one too. So, that's just kind of how these go. So, that's why I was like, it's really light. I just want you to kind of talk about it. Go ahead. For this one? Go ahead.
So what I did was I wrote down the formula.
Okay, what formula did you use?
The sector, which was pi times radius squared times that theta
Okay.
divided by 360, and that's supposed to equal
Wait, was this the formula or you divided it by 360?
divided by 360.
That's the formula has the 360 in it? Okay.
And I said that equal to 24.
And you set it equal to 24. Okay.
That was the area.
So let me kind of get some space on this one. So let me show you what I'm thinking. So it'll go like this, and we'll get a copy of this question. Yeah, that's better. So I'm going to add a page. So I'll just give you a little bit of backstory on this one, as far as what I know. And again, because I know we hadn't talked about this, but there's this big thing about getting stuff in a grade book. So I was like, okay, that's fine. So I'm just trying to be within compliance. I usually don't do the stuff this early, but we kind of got to do what we got to do. So now, say it says find the central angle theta who forms a sector of area 24 square centimeters. So say we have a circle, right? Just have a generic circle, and then if I can find the center, that would be great. So then we have some sector. I'm just drawing a random sector of the circle, something like this. So a sector of the circle. It says find the central angle theta. So the theta would be here, something like this, which forms a sector area. So the area in this case is 24 centimeters squared, and it says that the radius is 7 centimeters. So again, this was the open notes, right? So you can use your notes, right, or the book or anything of that nature. And it's, we're being really light. I just using it as an excuse or a platform to open up some discussion. So now, what's the basic shape of that sector? Yeah, something like this right now. It's close to a triangle, right? So if it were a straight triangle, what's the formula for area of a triangle? One half base times height, right? So area of if it were a triangle, it would be one half the base times the height, right? But right, our base is kind of curved, right? Because we don't essentially have a flat base. Like if we let like this guy be the height, it's like our base is not flat; it's curved. So we kind of have to adjust for that a bit. From what I remember, as far as the formula, this is off the dome. This is without looking at anything. I'm just kind of doing some backstory. So what would the height be in our context, based on our discussions before? What concept? What part of the circle would that be? The radius, right? So we can say that the height is the radius, right? Now the base, I think we did talk about something like that last time for the curve. This curved part here. How can we find that length? So let me see. I think this may have been where we stopped, but I'll just tell you now. So that green curve that you see is what we call arc length, right? So arc length. We're going to define arc length as S, which is the length of the curve around the circle. That's going to be r theta, where r is the radius times the measure of the central angle theta. So S equals r theta, and theta has to be in radians. So theta in radians, where theta is in radians, right? And again, I'm pretty sure we didn't talk about this last time, so you can give yourself credit for this one too. We're just using it as a platform to open up the discussion. So now, so we're gonna let that be our base. I think that's kind of how this goes. So instead of B, we're gonna let that be S. So then I'm under the impression that the area of a sector of a circle, so that's why I put the curve on it, should be 1/2, theta r squared, right? This is where theta is in radians. Again, theta in radians. Let's just try this out and see if it works. And then if it doesn't work, we'll make adjustments. Is this okay? So now, It says, let's see. It says, so we want to solve for theta. I think this is everything. I can't think of anything else. It says, which forms a sector area. So it says the area is 24 square centimeters and the radius is 7. So if we take this formula, we want to solve for theta. So we're going to say 1/2 theta. We said the radius was what? 7?
Yeah.
7. So we're going to say 7 squared. And we're going to set that equal to 24 centimeters squared. Is this okay so far? Okay. So then again, our theta, so this is going to give it to us in radians. And yeah, we want radians. So then we just solve for theta. So if we were going to solve for theta from here, what would we do? Put what in the calculator? We got one. It's kind of like if we had one. Yeah, we want to isolate the theta. How can we isolate the theta?
So divide all that
By,
by the theta. No way, you can divide it by.
we want to move things away. We want to move things away from the theta. Not subtract, but okay, if we do the 7 squared, that'll be
You divide it
49 times what? 1/2, right? Times theta. Okay, equals 24. So we have this number times theta equals 24. If we want to get the theta by itself, divide both sides by that and 1/2, right? So we got to say divided by 49. It's a couple of different ways, but it's essentially the same thing like this, right? So that way something divided by itself becomes 1. What we do on the left, we also do on the right. We could have simplified it further before going forward, but you know. So then theta is going to be 24 divided by 49 times 1/2. You can use a calculator at this point. 49 over 2, so it's going to become 48 divided by 49. I think that's about it. Let's see. Yeah, we're going to do decimals because it says type an integer or decimal, round it to 3 decimal places. Let's see. Hey Siri, what's 48 divided by 49?
48 divided by 49 is about 0.9795.
9795. Let me see. 9795. It says 3 decimal places. So what is this to 3 decimal places? 980, right? 0.980 radians. Okay. Let's just do a quick glance and see how do we do, and then we can open the floor for questions.
Wait, how do we get?
Wait. Let me make sure that it's correct. Make sure my logic was sound. So then number 2, 980 is correct. Okay. So now we can open the floor for questions. You can actually go ahead and give yourself credit for that one too, because I know there was a lot of stuff there that we hadn't talked about. You know, I was just trying to get a sense of, you know, what you guys have done since the last time. Go ahead.
How do we get 48?
The 48. Okay. So give me a color. What color are you feeling today? Brown. Okay. Give me a random object. What'd you say? A rag doll. What kind of rag doll? Just a rag doll. Which one? A shark. A rag doll shark. Okay. I know, right? I was like, you're making it difficult. Okay, so if we got a ragdoll shark, it's something like this, right? The shark, he got his fins, boom, boom, and then he has this. Something like that. And this is our ragdoll shark. Okay, so we want to take that, and we're going to let this be our cursor. Let's go style. Let's give it some thickness. Shrink it down some more. Okay. Anyway, this is just our cursor. Just something to draw your attention. Okay. Okay, so this, where's the formula? Right here. So this is the formula for the area of a sector, right? Where theta is in radians. Theta has to be in radians for this to work. This should be in your text. You know, I tried to give you a little backstory of how I feel like the formula came about, but it's really, you just need to know how to use this formula. Is this okay? So we're using this formula here. So then if this is the formula, we're solving for theta. They gave us the radius and they gave us the area. So then we plugged it in here. Is this line okay? Whoops. Is this line okay?
Oh, 48, 24.
Right? So at this point, right, we had 1/2 times theta times 49. So I could have gotten rid of the 1/2 first by multiplying both sides by 2, right? Because dividing by 1/2 is multiplying by 2. If we multiply both sides by 2, the halves are gone, and then this becomes 48.
Okay.
Right? So dividing by 1/2 is the same as multiplying by 2. That's where the 48 came from. Okay, so that one actually worked. Okay, any other questions on how we generated these numbers before I go forward? So again, you can give yourself credit for that, just trying to have a discussion. But it's a good idea. Every time we finish a section or start a section, you definitely want to go ahead and do that homework. Okay, like don't delay. Let's see. This one says, a water sprinkler sprays water over a distance of 50 feet while rotating through an angle of 130 degrees. What area of the lawn receives water? So I think we can use the same formula again, right? So let's look at it again. So say we're doing number 3. Let me go ahead and get some space. Matter of fact, let's go like this. We're going to move this up so that when we get a copy. Yeah, we're going to do it right now. So, I mean, again, you're here. I would just go ahead and give myself credit for this one, too, because it's the same kind of deal as the last one. So, you know, it just is what it is. Let me do it like this. Add a page. It's in the book. Yeah, you see it? Oh, also, let me show you something else about these kind of things. Maybe. I don't know that I'm going to be so lax, but, yeah, this is pretty much the format that I like to use. But yeah, I mean, where I'm kind of letting a lot of things slide right now because we're literally just starting, I probably won't be so lax going forward, right? Okay, let's do it like this. Crop. It's not, just be ready to kind of be accountable. That's all. Okay, and let's do one other thing. Come on. Crop. Okay. So, oh yeah, so we're still using the same formula. So under the impression that this formula goes, again, area of a sector is going to be, what do we say, 1/2 theta r squared, where theta in radians. Is that what we just said? Yeah. Pi r squared. Okay. Let's see. So then this one says the distance. So what is the 50 feet in our formula? What's the 50 feet in our formula? That's the radius. Okay, so r is 50 feet. What is the 130? Theta. So theta is 130 degrees. Okay, so then what do we need to do? The question is asking for what? What are we trying to find? The area, right? We're trying to solve for the area. So if we're going to use this information to solve for the area, what do we need to do?
Input 130 for the theta and 50 for the r.
Does everybody? Oh, okay. If you do that, what result do you get?
Wait, let me do it.
I'm probably. If you see something different, say something. If you see something, say something. What number do you get for the? What kind of result did you get? I'm curious.
162,005.
Is that reasonable for a sprinkler? So what kind of mistake could we possibly have made? What kind of mistake could we have made?
Must be the theta.
What about theta?
Wait, is it 130? Oh,
Yes, you do. Yes, you do. Don't give up. Don't give up. You're right there. You're knocking at the door of success.
It's the theta.
I will give it to you. It is the theta. What about the theta? What about the theta? 130 degrees.
Yeah, I don't think 130 degrees.
So then, what do we need to do with that 130?
We gotta change it to the radians.
There it is. They gave it to us in degrees. We need to convert it to radians. Remember, I said that formula only works if theta is in radians, right? So we need to convert. Okay. Go ahead and do it. So convert it. So we did a conversion. I think the first one, example 1, question 1, we did a conversion. Question 2, we used that formula. So put those together to answer question 3. So now I'm going to let the point stand. So even though I have a copy of your original, I know this discussion. So go ahead and work number 3. You can work together. You don't have to work alone. You can use your things, but go ahead and answer number 3, and then show your work and then grade it yourself. But this grade is going to stand. I'm going to let you grade it, but go ahead and work it first. So again, so for number 3, what are the 2 steps that we need to do? First, we need to do what? So we need to convert to radians, so from degrees to radians. Then we need to do what? Just use the formula, right? Okay. So take a moment to see if you can get that one. How do I say your last name again? Okay. Okay, have you all gotten a result? So just
I got 2.2.
what's your last name again?
Okay.
What'd you get?
I got 2 point. It's gonna be wrong.
That's
but
okay.
I got 2.2689, but if you run at 2.26.
Okay. Okay, let's see. So this is question. Okay, it says round to 2 decimal places, right? See here it says round to 2.
Oh yeah, so it's gonna be 2.267.
67. Okay. Okay. So does it as a group, as a class, do you all agree or disagree? Does somebody want to contest it, or
I got.
Let me see.
I don't know.
what? You got 1,000 something? Is that reasonable for the context for a water sprinkler? 1,000 feet. 1,000 square feet. 50 times 56. 2.2. So if it's 50 feet, right? If it's 50 feet, look, say it was a square, just using brute force logic. Say like the radius, one side was 50, this was 50. If it were a square, like say that was 90 degrees, what would be the square area if it was 50 by 50?
Yeah. Wait.
2,500, right? So then it could be 1,000, right? Is that right? Square feet, because we're talking about square footage. I'm just trying to get you to get a sense of, is the answer reasonable now? You got a different result? What result did you get? Huh? The 50? Yep, could be, yeah. Okay, you converted it to radians? Oh, the 2.27 was your radian result? Yeah, so first we want to find radians, right? So convert it to radians and then use that radian angle measure to answer the question, right? Okay, so does anybody in the house have a final result that they can back? No final result? Y'all should be able to do this. That's okay. It's okay if it's wrong. This is Mr. Is it Hightower? No.
Yeah, I'm Mr. Hightower.
So what result did you get?
2,837.5.
Okay. It says what? What's after the 5? This is 50. Okay. What is that? Square feet? Okay, I think that's reasonable, right? Anybody want to contest this result? Anybody got something different that they feel strongly about? For a final result, a final answer?
I guess. I got 73,513.27. Why you laughing? I know it's wrong.
I don't know what's wrong. I don't know. It's just 73,000. What'd you get? Keep going.
513.
513. Okay.
27.
Okay. Let's look at it. Any other results that we want to test? So we're gonna go together, but we gotta agree on a result. What'd you get? We want the final result for this one, the final answer. So first we convert it to radians, and then once we have the radians, use that to answer the question for the square, this area of the sector.
Why is this wrong? Why is this
It's
wrong?
okay. So this isn't. So we gotta. It's not about it being wrong. It's about why. For this discussion, why is it wrong? Like we got to answer the question, why are things the way that they are, as best we can, right? Because then once we know why, then we can say, okay, then we can kind of get to the bottom of everything, right? Let me work it before we glance at the answer. Any other results that we want to test out? Okay, so let me see. Now, if I were to do this, I'm gonna choose purple for myself. So we said what? First, we need to put it into radians, right? So we want to take this 130 degrees. We want to convert that to radians.
Okay, I did that right.
So then what is that? 180 degrees corresponds to pi radians. Okay? Is this okay? Okay. So since we have degrees on top, when we do the conversion, degrees need to be on bottom. All right? Okay. So then the units of degrees are canceled. So then we need to do, basically it's going to be 13 pi over 18. That's the exact result. That's going to be radians. I'm going to leave it like that. I'm not going to crunch that number until the end. So I'm gonna leave it exactly like that. Okay, I'm gonna leave that. Now that's my theta. So if that's my theta, we also have the radius there. So then the area of the sector should be 1/2 theta, which is this. I'm just leaving that number. I'm trying to keep it exact until the end. I'm just not crunching that number. And then r is what, 50? We're gonna say 50 what, squared, right? So let's do this. So hopefully this will work. Should work. Come on. Yes, let's get done. Let's get rid of all of this. Come on, let's close all these tabs. This one. Come on. Y'all are changing it up for real. Okay, so now let's see, how do we do? Let's reload and refresh. 0.5 times. We got 13 pi over 18 times 50 squared. Now the result that I get when I crunch these numbers is 28, 36, 16. That's only because I didn't round. So I would give this full credit because it's close. Only reason it's different because he rounded. But this is just when I did it. So when I did it, if I round to 2 decimal places, I'm gonna say this is approximately 2836.16. What are the units? Feet? So this is when I do it. Now, that's what I've done. That's what, as a group, we'll stand by that one. So you can all give yourself credit for that, because as a group, at least somebody got it. So then, So now let's look at the actual result and see how do we do. The 2836.16 is correct. So with this experience, if you were actually working on Pearson, Mr. Hightower, if you put that answer in, it would have marked it wrong. On an exam, more than likely, I'll make your exams multiple choice. So then if you got something like that, it would be close. So then you'd have to make an executive decision. But you see, I was able to get the same thing that the book has as a result. And so the difference between what you did and what I did, you more than likely used 3.14, which is a rounded version of pi, or you rounded somewhere early, right? Right, and then you cut it off, right? So the lesson is that the earlier we round, the more skewed our result is going to be. The goal, idealistically, we want to keep our numbers exact as long as possible until the very end. We typically don't round it to the end, right? That's how you get those numbers. So, but since we got somebody in the audience that at least got close, go ahead and everybody, you can give yourself credit for this one as well. I'm watching the clock, okay? Okay, so now let me pause for the cause and open the floor for questions for this one.
All right.
This is actually really good. I'm liking this. Go ahead.
Oh, I'm sorry. You go.
Whoever, y'all work it out.
So you went from 130 to 13 to 180 to 18, which is
Yeah. When you have the trailing zeros, you can just cancel off the trailing zeros as long as there's no decimal. You know what I mean? So like 130 divided by 180 is the same as 13 divided by 18. Yeah. Yeah.
That's what I was asking.
For the what part?
So let's say 13 divided by 18 equals the number 130 divided by 180. So it's going to be that number just with 2 zeros on it.
The last part. I just can't hear the 2 zeros part. What?
So I'm saying 13 divided by 18, the number that you will get will pretty much be, if you do 130 divided by 180, it's just going to have 2 zeros on it.
No, if you say 13 divided by 18 is the same as 130 divided by 180. Those answers are the same. Yeah, like you can do it in your calculator. 13 divided by 18, you get an answer. If you do 130 divided by 180, you should get the exact same answer. And it comes out of the following. So if we said 130 divided by 180, that's the same as 13 times 10 divided by 18 times 10. Is that okay? So then this is this. Is that okay? The 10s cancel. Yeah, that's.
See that the taking the zero off be throwing me off.
But does it make sense as to why I was able to do it now? That orange part at the bottom? Because 130 is the same as 13 times 10.
Yeah.
180 is the same as 18 times 10. So then let me show this other step. So then this is actually the same as this times 10 over 10. Something divided by itself is 1. 1 times anything is itself. All right, so for the orange bar is why we could just truncate the trailing zeros. That is to the left of the decimal. If we had the decimal, then that's different. It's a little, but this works as long as there's no decimal. You can just cut off the trailing zeros. Okay, so any other questions before we go forward? No, it just simplifies it because sometimes those zeros can make things more complicated, more likely to make a mistake. It just takes a little practice to see it. Go ahead.
Let's say it has zeros and then at the decimal point, it has 0 behind that.
Well, if it's all zeros, then a decimal with trailing zeros is the same as without the decimal. It's just if you have like other numbers on the other side of the decimal, it doesn't work. You see what I'm saying? Yeah, if the 8 is there, you can't. It's not a trailing zero any longer. But if you have point and then it's all zeros, you typically don't write it that way. Yeah. Okay, so we're gonna let that be. That was number 3. So then number 4. Yeah. So this is the one of the ones we. So okay. So So this thing today was just an attendance thing. So it was just see if you were here, because obviously we hadn't talked about a lot of this, and I didn't really want to make you responsible for it just yet. So you're pretty much getting credit for just doing it. I'll be aware of that. So let's go ahead and do this one, because this is, I think, one of the ones in the notes for today. Okay, you see where it says the ID, blah, 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 blah. You see that part? What does that mean? Where in the book the question is coming from, right? All right, okay. Let's drop this here. Let's get rid of this for right now. Let's add a page. I need some space, thank you. Right here, let's add a page. Okay, so let's look at this number 4. So again, it's just a quick gauge. I just wanted to see where everybody's at. So we have a city is due north of city A is due north of city B. Find the distance between city A and city B. Assume that the radius of the Earth is 3960 miles. So what we're doing, I know we hadn't talked about this one. So this is why I was like, for this assignment, you're pretty much going to get full credit. It's just something light. It's just a attendance grade and just a way for us to talk. So what this is, so if you imagine that we're talking about the globe, right? Let's do, I don't know, this color. We're talking about the globe. And then say, let me think about it. So say this is city A, and you kind of got to think 3D, right? So say this is city up. Here's city A. is due north of city B, right? Find the distance. And it gives us 46 degrees and 2 minutes north. So it gives us the lines of latitude. So if you imagine like, so the discussion in that we need to talk about, let me move these up a little bit. So if we consider like the equator, if we think about like the center of the globe, then if we look at, and let me kind of move this out of the way a little bit. So if we're looking at city A, we can consider the central angle made with, if we drew a line from the center of the globe to the equator, that would be that. And then we can draw another one here. And then we can talk about this like angle, right? We have like an angle theta based on A, right? So the position on the globe, if you have the line of longitude or latitude, I think it's latitude, but it's 46 degrees, 2 minutes due north. So that theta would be 46 degrees, 2 minutes for city A, all right? So then we can do a similar discussion for city B, and that line of, it should be line of latitude. So from the equator up to that city, horizontal circle, right, makes an angle of, the next one's going to be 19 degrees, 38 minutes for city B. So then we have basically two central angles. So if we were to take a cross section, like a vertical slice of this image, the idea is that city A is kind of making an angle like this. So here's city A up here, and the angle is 46 degrees, 2 minutes. That's city A. This is the equator. And then city B is kind of, if we did a cross section, is a lot thinner. Here's city B. This is the center of the earth, of Earth. This point here. Over here is the equator. This is the equator. It's the center. And now this one is making an angle of 19 degrees, 38 minutes. All right? So then the question, and it says that city A is due north of city B, so they're on the same line of longitude. So then, given this information, it says find the distance from city A to city B, right? So if they're on the same line of longitude, what could we do to find the distance between these two cities? If we were to kind of take these two images and lay one on top of the other, when you think of the letter B, what color comes to mind? Other than blue. Okay, we can do black. That's fine. So let's do style. We'll do black, right? So black will be for blue. Black and blue. Anyway, so if we were to lay these two images on top of each other, city B would be somewhere like this, right? And then you still have this, and you have this kind of thing going on, right? Where that angle is the 19 degrees, 38 minutes. So then my question is, how can we find this distance from A to B? From here to here.
Are we doing like time distance or like
Oh.
further? I mean,
Okay, so instead of worrying about the distance from A to B, let's focus on A first. So again, say this is A, right? So we have A is there, this is a curve, here's the center, and here's the equator. Tell me about this, that bold region. How can we find that distance?
using the formula.
Which formula?
1/2 stem. I mean, is it stem? Am I saying it wrong?
Th-
The little circle.
That's a theta.
A theta.
So that formula gives us the area of this shape. We don't want the area, we want the arc length, right? So we're going to use the arc length formula. The arc length formula, we mentioned it earlier today. I'm going to just say it again. So give me another color. When you think of A, what color comes to mind? What is that, orange? Okay. Orange, it's okay. So now, say we wanted to find that orange distance, right? We're going to use the arc length formula. S equals R theta. The arc length is going to be R times theta, yeah? So that's arc length formula. With, again, theta has to be in radians. This is what we were using earlier, all right? So if the orange is S equals R theta, and the black curve is also going to be a different S equals R theta, so we can find those two arc lengths and then do what?
Add them together.
Not add them, we want the distance between the two, so we're going to subtract them, right? We can find the arc length created by A, the arc length created by B, and then subtract those two distances. Let's start with A. So say we want to find the arc length of A. So that's going to be the radius of A. That's going to be the radius of the globe, which is the 3960. So the radius is 3960 times the theta for A. Oh, we got to convert. So this S equals R theta only works when theta is in radians. So we need to convert degrees, minutes, and seconds to radians. Okay. So let's go back. Let's do this. We're going to add a page. Nope, not there. Okay. So we need to convert these angles. They both need to be in radians. So 46 degrees, 20 minutes. So if we're focusing on part A, 46 degrees, 2 minutes, right? We need to convert that to radians. So right now it's in degrees, minutes, and seconds. I think now this one we were just about, either we had just started on it, we kind of touched this one last time. So right now it's in degrees, minutes, and seconds, right? We need to go from degrees, minutes, and seconds to decimal degrees. And then once we have it in decimal degrees, we're able to go into radians, right? So this is what we kind of did last time. So let's convert that 2 minutes. We need to convert that to degrees. 2 minutes. So now, how many minutes in a degree? 60, right? So then 1 degree is 60 minutes. The units of minutes cancel. So then 2 over 60. Let's see. Hey, Siri, what's 2 divided by 60?
2 divided by 60 is about 0.03333.
I'm going to just leave it at 0.3 bar. Degrees, right? So 2 minutes in degrees is 0.03 bar degrees. So then this theta is going to be 46.03 bar degrees. So then we need to go from decimal degrees to radians. How do we convert this to radians?
46, oh yeah, over 1, and then pi over,
Mm-hmm.
pi over 180.
Yes. All right. Units of degrees cancel. We're going to finish in the units of radians. Let's see. 1 over 30. So we really need to do this 46.03 bar times pi divided by 180. That's the radian measure. That's the exact amount if I don't do any rounding or anything of that nature. I'm going to just leave it like that for right now. So you can kind of crunch that number. Now, if you crunch that number and you want to use the decimal, just use the whole decimal until the end. Don't round it to the very end. So when you're crunching your numbers, just take the long decimal. I'm going to leave it like this because I know that's my angle measure in radians. I'm going to put my units of radians. But if you want to get a decimal, you can use the decimal, but take the long decimal. Don't round it to the end. Okay, so if this is my theta for A, and we want the arc length, so let me kind of get it right here. So then the arc length of A is going to be the radius, which is the 3960, times that angle, that radian measure, 46.03 bar pi over 180. I'm going to leave it exact. Okay, that'll give us the arc length. Let me let that one be for right now. So then we got to do something similar for part B, for city B. We need to convert that degrees, minutes, and seconds to decimal degrees, and then from decimal degrees to radians. 1938. So 19 degrees, let's clean it up. 19 degrees, 38 minutes. Mm-hmm. All right. So if we're focusing on that 38 minutes, we need to convert that to degrees. 60 minutes is to 1 degree. So then it's going to be 38 over 60 degrees. I'm going to leave that like that. So then theta is going to be 19 and 38 over 60 degrees. It's just the exact result. I'm just leaving it like that. I just added that to the 19. So then the arc length is going to be the 3960. Oh, we need to convert that to radians, right? So then we're going to say over 1 times what? Pi over 180?
Yeah.
Again, if you're using the decimals will work, but you got to use the whole decimal. Don't round or don't cut it off until the end. If you round early, it's going to skew it. So I'm doing my best to kind of keep it exact until the end. 1938 over 60 times pi over 180. Pardon? Okay. That's going to be radians. The units there are radians. So then the arc length for city B is going to be the 3960 times all of that. Again, this is just my attempt to keep it exact until the end. You don't have to do it this way. I'm just showing you that it's possible. Okay. So now we have the arc length for city A. We have the arc length for city B. So then we're going to say the arc length of A minus the arc length of B. I'm just going to subtract those two results. So what I'm going to do is take this. I want to copy, paste. I'm going to say that minus this one. This is what I'm going to type in. You don't have to do it this way. It's just, you can do it a different way. Just don't round it to the end. When you crunch these numbers, don't round it to the end. Okay, so I'm going to type this in my calculator. So I'm going to say the distance. Okay. So now let's see it in action.
Is there a way you can put like a little line over the 3 in the calculator?
You can write it as a fraction. So we did, how did we get that? We did that's 1 over 30. So I'm gonna incorporate the 1 over 30. So I'm gonna type this in the following way. So let's see, we got the 3960 times. Now the first part is the 46 plus the 1 over 30. That's fine. Times pi. I'm going to close off the top. Let me think about it. That should be okay the way I have it written. I'm going to say divided by 180. That should take care of the orange part. I'm going to say minus. Now let's see. Let's focus on the top. We got the 3960 times. We got this 19 plus 38 over 60. That closes that off. I'm going to say times pi. And then I'm going to close off the top and say divided by 180. Hopefully I use my parentheses properly here. Now I get a result of, what is this, miles? Let me see, 1824, 1,800 miles. Is that reasonable? I think this might be okay. Let's kind of go with it and see what happens. So I get a result of 1824. It says to the nearest mile, so 1825. Let me see, how did I do, or how did we do? Anybody get a result close or different? Anybody get something at all? So again, I didn't round any of my results. I tried to keep them as exact as possible. Let me see how did we do, and then we can. You saw for like the orange. But then you got to go back and do the same thing for B, and then subtract the two results. What result did you get for part A? You should get something larger than 1,800.
33,000.
Yeah, that's reasonable, right? Because if we say your number minus whatever B is, it is possible that you can get this 1825. Let me see. Let me look at the result to see if 1825 is good. 1825 is good, all right? So again, you don't have to do it this way. I'm just showing you that it's possible. The key take home here, the key take home with this one, let's do like this. I'll do this color. The key take home with this one is being able to do this. Converting between those units. They gave us the theta in degrees, minutes, and seconds. First, we have to convert it to decimal degrees, and then from decimal degrees, we have to convert it to radians. All right? So then once we have our theta in radians, we just use arc length. S equals r theta. Okay? I know it looks intimidating.
Oh, I got you.
Okay, it's not as bad as it looks. I promise you. It looks intimidating, but it's not that bad if you actually give it a go. Okay. 1825 is right. All right. Is that okay? You got it? Okay. So I know of at least 2 different groups in the audience that got it. So team up. It's very important for you to team up and work together.
There's a lot to type in, but I got it.
But you got it, right? That's the whole point. Like it looks intimidating, but it's not that bad. So it was just two main ideas. Arc length, S equals R theta. And then, but if we're using S equals R theta, theta has to be in radians for this to work. All right? Okay. So let me pause for the cause. Other questions about this one before we go forward? We got one more. But you can give yourself credit. Again, I'm pretty much going to give everybody credit because I know this is a little bit intense, you know. And it's not always like this, but, you know, I just kind of had to kind of talk about it. Let's do the last one. And I'll load a copy of this where you can access it. Okay, so we'll let this be we're going to go ahead and do this one. To approximate the speed of the current of a river, a circular paddle wheel with radius 5 is lowered into the water. If the current causes the wheel to rotate at a speed of 15 revolutions per minute, what's the speed of the current? Let me think about this one. So this is angular rotation. To approximate the speed of the current of a river, radius 5 is lowered. S equals, is it arc length? Angular velocity? I'm going to look up the formula for this one just to kind of look at something really quickly. So let's go like this. Anybody got their book handy? Ready to go? Let me see it. Oh, good chocolate. Oh, no. So again, where in the book is this one coming from? Question 115, right? So this is about angular, let's see, here it is, right here. Finding the linear speed of an object traveling in a circular motion. It says, to approximate the speed of the current of a river, the circular paddle wheel with a radius 5 is lowered. Let me see. Not the area. So it's either finding the linear speed of an object traveling in a circular motion. Let me see. Hang tight. So it's right here. Then the linear speed of the object is defined as the velocity equals s over t, where s is the arc length. The angular speed of the object, okay. So let me look at one other thing. Angular speed is the way angular speed is the way the turning rate of an object is described. For example, blah, blah, blah. There is an important relationship between linear speed and angular speed. Linear speed, which is v, which is s over, which is this. So the linear speed equals r times omega. Okay, so now if we have this circle, it says to approximate the speed. So I'm under the impression that we want to find the linear speed because we want to find the speed of the current. We have a circular paddle wheel with a radius of 5 is lowered into the water. It says that the current causes the wheel to rotate, so we have the angular speed of 15 revolutions. So if we go to the email, actually I got it here. Let's pull it up right here. I want you to see this. Precalculus, right? Right triangle approach. And this is right here, 5.1. This is page, is this y'all's book 395? Come on. Right here. Okay, thanks. So what this one is referring to is like we're talking about linear speed of an object traveling in circular motion. It says, suppose that an object moves around a circle of a radius r at a constant speed. If s is the distance traveled in time around the circle, then the linear speed of the object is defined as this. So the linear speed is going to be the arc length over t, right? So given arc length and given the time, we can get the linear speed. As this object travels around the circle, suppose that theta in radians is the central angle swept out in time t. So then we can also talk about an angular speed, omega, right? Of this object is going to be the angle theta swept out divided by the time. So the angular speed is going to be omega over t. Angular speed is the way the turning rate of an engine is described. For example, an engine idling at 900 revolutions per minute is one that rotates at an angular speed of the following, right? So you know how it's rotating. So then we have this relation between linear speed and angular speed. And you see it here. It says that linear speed v, which is s over t, but then s is the arc length, which is r times theta. So then we also said that theta over t is our angular speed. So then the correlation between linear speed and angular speed is this last bar that you see here. The linear speed is going to be r times the angular speed. Okay, so now let's see if we can use this to answer the question. Let's go back. So let's see, first let's go here and let's try this one. The linear speed is going to be s over t. Let's see if we can do that one. Come on. So linear speed is s over t, arc length over time. Approximate the speed of a current of a river paddle with a radius is 5. So it says that the radius is 5 feet. Is lowered into the water. The current causes the wheel to rotate at a speed. So that sounds like angular speed, omega. 15 revolutions per minute. Okay? What is the speed of the current? So since they gave us the angular speed, instead of using s over t, we're going to use the other formula where linear speed is going to be, I forgot, just that quick. Mm-hmm. Hang on, I'm going right back to it. 5-1, let's go here. Oh, 5-2, so let's go here. Yeah, it's right here. That's omega.
It's a Greek letter, ain't it?
Mm-hmm.
I thought it, yeah.
It's lowercase. Lowercase omega. All right? That's what we're looking at. Oh, that's what we wanted to do today. Okay, I see. Back up. We'll just get that going next time.
That was the easiest thing I ever learned.
I mean, that's here, but we're not there yet. Right here. R times omega. All right? So then the linear speed is going to be 5 times basically the 15. So what is that, 50, 65? No, 75?
Yeah.
What are the units there? Feet per minute? Let's see, how do we do? I think that's right. Number 5. Let's go back. What are we missing? Miles per hour. Oh, okay. Oh, we got to do some conversions. Okay. Let's back up. So let me make sure again. Approximate the speed, 15 feet. Revolutions per minute. What's the speed of the current? So we said, no, we got what? When we did this, we got what, 75? We got what, feet per minute? So we want miles per hour. Okay, let's try converting this to miles per hour. But, well, I mean, first I'm just trying to think, will this make, let's just do it and see what happens, and then we'll come back if it's not right, all right? So we need to convert 75 feet per minute to miles per hour. So if we have 75 feet per minute, all right, we're going to say times. Anybody know the conversion for feet to miles? If you didn't know it, it's okay. I would give you this. Like, so the conversion from feet to miles, 5,280 feet corresponds to 1 mile. All right, so now the units of feet cancel, so that one's done. We need to convert minutes to hours. How many minutes in an hour? 60 minutes is to 1 hour. Okay, so the units of minutes are gone. Now we're left with miles per hour. So then we need to say 75 times 60 divided by the 5280. Let me see. Hey Siri, what's 75 times 60 divided by 5280?
75 times 60 divided by 5,280 is about 0.8522.
She said approximately. This should be miles per hour. Let's see how do we do now. 8522. 5.35. What else are we missing? Maybe not. Approximate the speed of the current of a river, circular paddle, this radius is lowered into the speed. The current causes the wheel to rotate at this speed of the current. Okay, let me look at one other thing. I'm going to go here. Again, now for the following is why I vouch for Pearson. What's the time? I'm watching the clock. Yeah, I can see it. Are you not going to work?
Oh my God, that's what I love about Apple. Especially when you gotta like purchase something online. All you gotta do is put your fingerprint in. Oh, thank you.
Yeah. How's it going? So let's look at it. Actually, no. Let's back up.
Samsung and LG got their own thing.
Okay. Let's do like this. And then let's go like this, and let's view it. Okay, so here's the same thing, just different numbers, and we can kind of figure out where we're making our mistakes. So it says the angular speed, yeah, we got that part right. Angular speed of the paddle is 15 revolutions per minute, so I know we got that one. Revolutions. Okay, so we needed to convert that to radians per minute. So that's revolutions per minute. Okay, so that was one thing, right? So we had to convert that to radians. So that's like our theta or omega, that's our angular speed. So they gave it to us in revolutions per minute. We had to convert the revolutions to radians. So like, you know, you can almost go to degrees and then from degrees to radians, but you see the conversion there. So that was the main thing, was just that conversion. To find the linear speed, I think we had that part right? R times omega. So then we got that. So then we would have that feet per minute. Yeah, so the only thing that we were missing, so we actually did it right. The only thing that we were missing was converting the angular speed. It had to be in radians first, right? That was the only thing that we were missing. So let's actually do that for hours and see if we can clean it up. So if we were to go back, we have to convert that 15 revolutions per minute, right? So we have to convert that to radians. So let's do that here. I'm going to let this be. I'm going to work a different color. We have what? 15 revolutions per minute.
Yes.
Okay, let's do this really quickly. What's the time? I see the clock. So if we have 15 revolutions per minute, again, this is omega. So one revolution, okay, so let's convert this to radians. So then what? One revolution will be how many radians?
One revolution would be 59.
It should be 2 pi, right? Because half a circle is pi radians. So then one revolution would be a complete around the circle should be 2 pi. Let me do a quick glance just to make sure so I don't waste any more time. Right there, you see it right there. One revolution is 2 pi radians, right? Complete lap around the circle. Does that make sense?
Yes.
So revolution is 2 pi radians. So then now we'll be in the right units, right? Revolution is gone. So then 30 pi radians per minute. Okay. So now we got that in radians. That's like our angle or our theta. So then we said r times omega. So the linear speed is going to be r omega. The radius was what again? 5?
Yeah.
5 times 30 pi. That should be 5 feet. So the units are going to be feet per minute. 150. 150 pi feet per minute. So then I think we have to convert that to miles per hour. Let's convert that to miles per hour and see if it works. So 150 pi feet per minute times. We said that 5,280 feet corresponds to 1 mile. 60 minutes corresponds to 1 hour. Okay, I feel better about this. So then let's crunch this number. This is going to be approximately 150 times pi. Okay.
What is that at the top?
Wait, let me.
Next to the one?
1 mile? Yeah. Okay, let me see if this works. Hey Siri, what's 150 times pi times 60 divided by 5280?
150 times 3.1415 times 60 divided by
There we go.
5,280 is about 5.3549.
And then it probably says 2 decimal places. 2 decimal places. So 5, which is approximately, what are the units here? Miles per hour. Okay, I know that was a little bit roundabout. You have to just kind of bear with me. But, and I think this is actually open. So this quiz that we took just now, I went on and opened it on Pearson, right? So I know we kind of had our experience with it, but this is actually open on Pearson. I'm kind of okay with that idea, opening things up on Pearson a little bit ahead of time. Some of the things. Go ahead. Yeah, you would have to create an account. It's to keep it free. When they prompt you to pay, at the bottom of that screen, it says get 14 days of free access. So then just go ahead and sign up for the 2 weeks of free access. At the end of the 2 weeks, it'll lock you out to just gain. You're going to lose all your information, but to gain access back, just create a different account with a different email. And then you can get another 2 weeks. And you can do that all the way until the end. Yeah. So you can actually access Pearson for free where they'll explain this stuff, you know. So, but again, so for this one, we had the right idea, but the thing that we were missing, we had the wrong units for our omega. We had it in revolutions per minute. We had to convert the revolutions to radians. Yeah, radians. Yeah. So that's where we made our mistake there. Okay, well, that was a fun little day, but we needed to talk about it. That was more of 5.1. We still have. Let me see. We got 20 minutes. So let's go ahead and take the remainder of class to go ahead and finish talking about 5.1. We actually talked about a lot of stuff here in 5.1 that we needed to talk about. So that's why I kept going with it, right? So I'm going to go ahead and load a copy of this for you all. I'm going to send it to Box. Let me see, the folder. So this is the fall, pre-cal, the course, and let's just do quizzes. I'm going to put it there, all right? So I'll make sure that everybody gets credit for this one. I had to update my grade book. But yeah, I'll make sure that everybody gets credit for this. And I actually have a copy of who was here. Yeah, it's a quiz, but it's just you were here. We discussed it, so I'm giving you credit for it, right? So I'll load a copy. I'm loading a copy of this for you all to use. It has the solutions at the end. We still have like 20 minutes, so we're going to go ahead and kind of keep talking about 5.1. We're going to open up the PowerPoint and take a look at that. I think there's something else I wanted to mention. Okay, so let's look at this. So we didn't finish that one, so let's back up. Come on. So let's go back. Where is it? Box, right? Precalculus. Okay, let's go like this then. Morning. Okay, so let's, anybody know where we left off? radians.
He was on converting the degrees to minutes and seconds. I mean, converting minutes and seconds.
Okay, so that's what we took. We did some practice today. So we converted like degrees, minutes, and seconds to decimal degrees, and we converted decimal degrees and vice versa. So we're gonna let that be. So we did some of that practice today. I'm gonna kind of brush through some of this today. So we're really introducing radians today. This is why I'm giving you all credit for that assignment that we just did. So let's start off here. So we have that a central angle is a positive angle whose vertex is at the center of a circle. Let's see. Okay, so say we consider a circle like this, right? Where we have a central angle. A central angle is an angle whose vertex is at the center of the circle. And we consider the circle with a radius of r, right? So we kind of had some discussions today about arc length. So we want to also consider the sector formed whose arc length is also r. So we have the radius of the circle is r, and the curve, the length of the curve made by the sector is also r. Does this make sense? It's almost like an equilateral triangle, but not quite, right? So the radius is r and the curve is r. So we're just considering a sector made by that. So now, what we're going to say that this angular measure, we're going to consider this as 1 radian. So if we make a sector where the length of the arc is the radius, the length of that curve is the same as the length of the radius, that angle is what we call a radian. You don't need to know all that. That's just what we mean by the definition of a radian. So if we were to kind of put all of those like side by side going forward, let me see, where is it? Well, you would get just about like just beyond 6, just 6 point something, because you know if that's a complete revolution around the circle is 2 times pi, so it's going to be 6.28 whatever. So you can do just beyond 6 of those if you put them side by side to go all the way around the circle. So that's just a little bit of backstory on what do we mean by radian, okay? So you don't really have to worry too much about that. It's just a little bit of backstory. We actually talked about arc length today, right? So this is where this formula S equals R theta is. The arc length formed by central angle theta is going to be R times theta, where theta has to be in radians. We saw today on a couple of different examples where if that theta is off, or the angle, if it's not in radians, it's going to throw things off. So it has to be in radians in order for this formula to work. Okay, so we talked about that. It says find the length of the arc of a circle whose radius is 4. They gave us this angle is this. So we just said that arc length is S equals R theta. So we would just say R times theta. Theta is already in radians in this case, so we got lucky. So then it's just 4 times that. So this one was okay. Converting from degrees to radians and vice versa, we actually just did this as well, okay? So 1 revolution around a circle is 360 degrees, and that's equal to 2 pi radians, all right? So 1 revolution is 2 pi radians. That's also 360 degrees. So that if we cut those in half, then 180 is going to be pi radians, all right? But we've already talked about this today. So the conversions from degrees to radians and vice versa is the pi over 180 degrees. Is this okay so far? I know it's a little bit choppy and all over the place, but is it okay? So this is what we did today. This is actually it should be on Moodle. If you want to take a picture, you can. Yeah, but this stuff is on Moodle. I just pulled this off of Moodle. Yeah. Or it should be on Moodle. If it's not, I'll make sure that it's there. So we did some conversions. You can actually practice here, but we did some conversions today during our examples. For instance, if we wanted to convert that first one to radians, to go from degrees to radians, let's do it really quickly. So, what color are you feeling? Peach. So, I'm going to use this one since that's the closest one to peach. I saw the other one, but that's a highlighter, yeah. Okay, so say we want to convert 45 degrees to radians. What's the conversion here? Times. Yeah. Why is the 180 on bottom? Degrees, right? Since we're going from degrees to radians, when we do our conversions, since we have degrees on top, we have to put degrees on bottom so they cancel. Right? So that's why this one is done this way. So then the final result would be 45 times pi divided by 180. You just have to crunch that number. Hey Siri, what's 45 times pi divided by 180?
45 times 3.1415 divided by 180 is about 0.7853.
Do they want the units? They might. That would be radians. If they want exact, hey Siri, what's 45 divided by 180?
45 divided by 180 is 0.25.
So more than likely they want the exact result. All right. The exact is the pi over 4. The approximation, you just say pi divided by 4. You get that decimal. Let's see how do we do on this one. See pi over 4 radians. Is that okay? Let's do another one. 45 divided by 180. Yeah, okay. Okay. Let's do another one really quickly. Let me see. We got 10 minutes, okay. So then for part B, we want to convert 210 degrees. We want to convert that to radians. Again, we're going to put it over 1. We're going to say times. Times what again in this case? Pi over 180. All right. So again, this is 210 pi over, again, units of degrees are gone. 180. What can we do with the trailing zeros? Yeah, we can get rid of them. They're both divisible by what?
By 10?
Well, we did that one already. We did that already. So we got 21 over 18. They're both divisible by 3, right? What's 21 divided by 3? 7 pi over 6. I think that's correct there. Okay. I'm going to screenshot this. Yeah, let's screenshot this. And let's just add this. Let's share. Notability. No. We wanted the exact result, and not an approximation. So I just went on and added that slide to what we were doing earlier. I'm gonna hit done, delete. Okay. So we at least have a copy of that. I'm going to clear this out. Anybody need a picture of this at all before I get rid of it? So we said 7 pi over 6. I think we confirmed that one already. Do we need to do the rest of them? Okay.
Well, wait, yes, just for practice. That negative 60 is.
Okay, let's just go ahead and do it. Oh, is it? Where's the? They did it already. Okay. Well, it's the same kind of deal. So if it's negative 60 degrees, we want to convert it to radians. What would we multiply by? Pi over 180. So then 6 over 18 becomes
6 over 18.
1 over 1 over negative
Pi over 6?
6 over 180. We're just doing it in a. What's 6 divided by 18? What's 3, right? 3. 1 over 3. So negative pi over 3, right, for that one? Okay. And then the last one is 100. So if we're converting that, we're going to, again, multiply by pi over 180. So that's 10 over 18. They're both divisible by what? 2. So it becomes what? 5 pi over 9? 9, right? Again, we're doing this in our head. You don't have to do it in your head, you know. So now that was going from degrees to radians. Suppose we wanted to go from radians to degrees. Say it was something like 2 pi. Say we went from radians to degrees. I think that's the next one. So if we want to convert these to degrees, what do we multiply by? Does that make sense? 180 divided by pi. We have radians on top. When we convert, we're going to say times 180 over pi. Okay, let's do it really quickly. What color are we filling? Okay. So for part A, we have pi radians over 4. We're going to say times. We said what? 180 over pi. That's my beautiful 180. (180 over pi radians, right? Radians cancels radians, 90, 45 degrees, right? Okay. Let's go ahead and do B. Walk me through this one. What are we doing here again?
180 over 580.
Okay, so then what happens?
And it's gonna be, yeah, over 6.
Over 6. So what's 180? What's 180 divided by 6 first? 30. What's 30 times 7?
210.
210. 210 degrees. Let's finish it, then we'll check at the end. C. Negative pi over 3 times what? All right, degrees. So then, keep going. Negative 60 sounds okay. The time, we got like 5 minutes. We're about to get out of here. And then part D. It has 2.5 radians, right? So then we're going to say this one is times 180 degrees over pi radians. So what cancels here? What persisted here that didn't persist in the others? The symbol pi, right? So then when we crunch it, it's going to be 2.5 times 180 over pi. Probably not. Probably just crunch. That'll be degrees. Yeah, you typically would find that number. We got that one, we got that, and then that approximation. Well, yeah. Yes. Yeah, I'm gonna leave it at that. I mean, but usually we have like instructions that'll say round to so many decimal places or whatever. Yeah. Okay. We'll talk about this. These are some common angles and degrees and vice versa, or angles and degrees and radians. We'll come back to something like this. This is the one that we did. So I know this example's here. This is the one that we did on the quiz. All right, so it's an example in the text, but we already did this one with all the nuances and everything. So this is the image that I was trying to get you to see. The lines of latitude. And then you could talk about the central angle made between those cities or whatever. Okay, so here's a digital explanation. What's a good idea for this one, after you kind of digest the way we did it in the quiz, see if you can answer this example without looking at the things. Like take what we did earlier and see, can you use what we did earlier to answer this without looking at the answer. Get an answer first yourself and then try to compare the way that the book does it. Right? See if you can do it. But again, the goal was to go from degrees, minutes, and seconds to decimal degrees.
Okay, yeah.
And then decimal degrees to radians, and then arc length, S equals R theta. All right? It's just those two ideas. And then subtract the two results, right? We talked about area of a circle, a sector of a circle. 1/2 R squared times theta. I think that's what we did, yeah. And then I think we've already worked an example. So here's another one if you wanted to practice. Circular motion. Really quick, I want to read this one. It says, suppose that an object moves on a circle of radius r at a constant speed. If s is the distance traveled in time t on the circle, then the linear speed v of the object is defined as this. So where the linear speed is going to be the arc length divided by the time. Okay, so that's the formula that we have for linear speed. The angular speed, omega, the Greek lowercase letter omega, all right, of this object is the angle theta measured in radians. Remember, we worked it, so we had to put it in the right units. Swept out, divided by the elapsed time, so it gives us this. So the angular speed is going to be theta divided by t, where theta is in radians. So again, something like this, you just need to know how to use it. I don't want you to try to, I mean, you can commit it to memory, it's not a lot, but the main thing here is knowing how to use it and being clear that theta needs to be in radians. Theta needs to be in radians. And then, so then we notice this relation between linear speed and angular speed, where linear speed is going to be r times omega. Okay. So here's another example. I would say give this a go. See if you can do it on your own as well. And it's similar to what we did in the quiz. Okay, so then that quiz, all I did, I went to 5.1 and I just chose some at random. I didn't like intentionally choose any. I wasn't meticulous. I just chose some at random and that's how it came out. And then, you know, it's kind of my own thing to kind of see, okay, well, where am I? Let me kind of switch back to here really quickly. Come on. There it is. So we have a copy. We have some notes there. So that was that. I'll make sure that everybody gets credit for attendance. I have who was here today, so we don't have to worry about that. There should be questions, I know, but that is what it is. But it's not like that all the time. It's just like that topic is just kind of like that. Okay, are there any other questions before I let you go for the weekend? So it's a good idea to go ahead and move into section 5.2. All right, go ahead and start on that. Go through the examples as best you can. If anything is not clear, email me. I think the homework is already posted. I know the homework is on Moodle, and I'm pretty sure I made it available on Pearson as well. Okay, if not, just email me and we can kind of go back and forth. Okay. Okay. Have a great weekend. I will see you all Tuesday. Okay. Let's shut them down.